Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know, there is a very specific, a very human bias when it comes to exploration.
Oh, yeah.
Yeah, I mean, when we look for anything, treasure, secrets, even just, information, we tend to look where the light is.
Right, the old joke. The drunk guy looking for his keys under the streetlight.
Exactly. Not because that's where he lost them, but because that's the only place he can see.
It's a survival instinct, really.
Yeah.
We're visual creatures. If something is dark or buried or hidden behind a curtain, our default assumption is that there's nothing there.
Or at least nothing worth the effort of trying to see it.
Exactly. We prioritize the visible. The invisible, well, that requires a whole different set of tools.
And in astronomy, that bias it's a killer. Because the universe is fundamentally a dusty, messy place.
Incredibly messy.
There are entire galaxies, whole chapters of cosmic history that are basically locked inside these giant vaults of gas and dust. And for the longest time, we've just been staring at the vault door.
And guessing, which is, rarely good science. You can measure the heat coming off the vault, maybe, but you don't actually know what the engine is inside.
Is it a star factory? A dying quasar? Something completely new, you just don't know.
We've had models, of course, lots of them. But a model without direct observation is, at the end of the day, just a sophisticated wish.
Well, today's discussion is about what happens when you finally get the key to that vault. We're looking at a paper published in Nature Astronomy in February 2026.
Yeah, it's a big one.
It really is. It's a study that takes the most advanced telescope ever built, points it at one of these locked doors, and essentially turns on the X-ray vision.
And what they found inside wasn't just, oh, look, there's a supermassive black hole. I mean, we kind of knew that already.
We expected that part.
Right. The real surprise was the chemistry. It completely changed our understanding of how organic matter, the building blocks for us, behaves in the most extreme environments in the universe.
And that's the hook for me. We're not just talking at gravity and physics today. We are talking about a chemical factory. We're talking about the ingredients for life being cooked up in the last place you would ever think to look for them.
It's like finding a gourmet kitchen inside an active volcano.
That is a surprisingly good analogy.
It really challenges that whole warm little pond idea we all learn, the Goldilocks model, that life ingredients need a calm, quiet, gentle place to form.
This study suggests they might actually be born in the fire.
Forged in it, yeah.
So let's lay out what we're looking at today. We have the main paper from Nature Astronomy, which was led by a team from the Center for Astrobiology, that's CAB, and CICI INTE.
And we also have the crucial modeling data that came from the University of Oxford.
And that modeling is key, isn't it? Because that's where the mystery really kicks in.
It is. The observational data told them what was there. The models told them that it shouldn't be there. And that gap, that discrepancy, that's where the discovery is.
I do love a good scientific paradox. Okay, let's start with the target. We're not looking at Andromeda or some famous galaxy. We're looking at an object with the very catchy name of IRACE, 072510248.
Rolls right off the tongue. But that IRACE part of the name actually tells you a lot of the backstory.
IRACE, that was the infrared astronomical satellite, right? Back in the 80s.
That's the one. It was the first mission to do a full survey of the sky in infrared light. And it found all these objects that were just blazingly bright in infrared. But when you looked with a regular telescope, you saw almost nothing.
They gave them a name, didn't they? URG.
URGs, yeah. Ultraluminous infrared galaxies.
So to a normal telescope, this thing, IRACE 07251, it looks like, just a faint smudge.
A very faint dark smudge, maybe a little reddish blob if you're lucky. But if you could see and heat in infrared, it would be one of the brightest things in the sky. It's screaming with energy.
And that energy, that visible light, is being trapped.
Exactly. Trapped behind just vast amounts of gas and dust.
Okay, so let's get into the specifics of this galaxy. The paper describes a very particular architecture right at the nucleus. It's not just a big blob of stuff.
No, it's layered. Think of it like an onion, right at the very center. At the absolute core, you have what they call the hot component.
The engine room.
The engine room. It's the immediate area around the supermassive black hole. Incredibly dense, chaotic, super hot. In their diagrams, it's this deep, dark red.
Okay, so that's the core. What's the next layer out?
The warm layer. The gas density drops a bit here, but it's still extremely energetic. This is where you find what they call gas phase molecules just zipping around. It's a bit cooler, shown as orange and yellow.
And then wrapping the whole thing up.
Is the cold envelope. This is the shell, a huge, thick shell of dust, different kinds of ices, and cold gas. And this is the part that acts like a blackout curtain.
The vault door we were talking about.
Precisely. For decades, astronomers have been trying to get a clear look through that curtain to see what the machinery inside is actually doing.
Which brings up the obvious question. We've had powerful telescopes for a while. We've had Hubble for decades. Why couldn't Hubble just zoom in and see through the curtain?
It comes down to the physics of light waves. Hubble mostly sees invisible light, the same stuff our eyes see.
The rainbow, Roy G. Biv.
That's it. And the problem is that the dust grains floating around in space are roughly the same size as the wavelength of visible light.
So they block it.
They block it perfectly. When a photon of visible light hits a dust grain, it either gets absorbed or it scatters. It's like driving into a thick fog with your high beams on. The light just stops. It creates a wall.
So Hubble looks at IRA 07251 and sees a wall of dust.
A dark, impenetrable wall. To see through that fog, you need light with a much longer wavelength. Light that can essentially, snake its way around those dust grains without bumping into them.
You need infrared.
You need infrared.
And that brings us to the hero of the story, the James Webb Space Telescope.
JWST, the machine that was literally built to see the invisible universe.
We talk about this telescope all the time, but I think it's worth pausing on why it's so perfect for this exact job. It's not just about having a bigger mirror than Hubble, is it?
Not at all. It's the instruments.
Yeah.
And the fact that the telescope itself is incredibly cold, so it doesn't blind itself with its own heat. For this study, the two key players were NIRI and NRSpec.
NRI is the mid-infrared instrument.
Correct. And NRSpec is the near-infrared spectrograph.
Yeah.
And by using them together, the team could look at a very specific slice of the light spectrum, from about 3 microns all the way out to 28 microns.
Okay, so why is that range 3 to 28 microns the magic window? Why not 50 or 100?
Because that range is the fingerprint region for organic chemistry.
Right.
This is really, really important to get. Molecules aren't just static little balls. They vibrate, they stretch, they rotate.
They're dancing.
They're constantly dancing. And every time they make a specific move, a stretch, a bend, they absorb or emit light at a very, very specific frequency.
Like a tuning fork or a musical note.
It's exactly like a note. A methane molecule sings at a totally different pitch than a benzene molecule.
Yeah.
And it just so happens that all those unique notes, those chemical signatures, they fall almost entirely within that 3 to 28 micron window.
So if you want to listen to the organic chemistry station, you have to tune your radio to that specific frequency.
And for the first time in human history, with JWST, we had a radio that was sensitive enough to pick up that faint signal from a galaxy millions of light years away.
It's incredible. The program ID for this was JWST GU3368. They pointed the scope, opened the shutter, and let those infrared photons, which had been traveling for eons, finally hit the detector.
And the data they got back wasn't just a pretty picture. I mean, they did make a nice false color image using different filters to help visualize the structure.
Right, I saw that. They used blue for 2 microns, green for 2.77, and red for 3.56.
Yeah, that helps you see where different materials are. But the real treasure, the scientific gold, was in this spectrum.
The squiggly lines, the graph with all the spikes and dips.
That's where the chemistry lives. Each one of those spikes is molecules shouting, "I'm here."
So let's open the box. They peered behind the curtain into the heart of this shrouded nucleus. What did they find? The paper makes it sound like they found a chemistry set that just shouldn't exist there.
That's a good way to put it. They found an inventory that was, frankly, shocking. In these incredibly high-energy environments right next to a supermassive black hole, you expect fragile molecules to just be ripped to shreds.
Right. You expect to see just, like, individual atoms, maybe some really simple, tough molecules like carbon monoxide.
That was the prediction. But what they found was, and this is the quote from the paper, an extraordinarily rich inventory of small organic molecules.
Okay, let's run down the list. What was on it?
First up, benzene, CAJ.
Benzene, that's the ring, isn't it? The hexagon of 6 carbon atoms.
Classic aromatic ring. It's very stable, which helps explain why it can survive, but it's also the fundamental building block for much larger, more complex structures called PAHs.
So finding benzene is like finding a perfectly formed brick. It tells you that you're not just looking at a pile of sand, you're looking at something that has structure.
Precisely. It's the scaffolding for more complex chemistry.
Okay, benzene. What else was in there?
They found the entire acetylene family. They found acetylene itself, which is C-Euros, then diacetylene, C-Euros, and even triacetylene, CAers.
Wait, so they're not just finding a molecule, they're finding a progression. The chain is actively growing.
It looks that way, yes. Finding that sequence 2 carbons, then 4, then 6 is a huge clue. It tells you that carbon atoms are actively linking up. They're polymerizing, building longer and longer molecular skeletons.
And this is happening in the middle of this chaotic, high-radiation storm around a black hole.
In the heart of the storm.
Yeah.
They also found plenty of methane, CH air, which is a classic, simple hydrocarbon. But the real headliner, the detection that got all the astrochemists talking, was the methyl radical.
Okay, you're going to have to help me with this one. To a non-chemist, CH sounds almost exactly like methane, CH. It's just missing one little hydrogen atom. Why is the radical part so important?
It's that missing hydrogen that changes everything. A stable molecule, like methane, is. It's chemically satisfied. Its electrons are all paired up. It's happy. It doesn't really want to react with anything.
It's inert.
Mostly, yes. But a radical, because it has an unpaired electron, is chemically anxious. It is incredibly reactive. It is desperate to grab onto something to complete its electron shell.
That doesn't stick around for long.
On Earth, if you create a methyl radical in a lab, it vanishes in a fraction of a second. It just instantly reacts with the first thing it touches. It's a chemical ghost.
A ghost. I like that. So finding a whole population of these ghosts floating around in deep space is weird.
It's extremely weird. It implies that there must be some process that is producing them constantly and at a very high rate. You're not seeing an old relic. You're seeing the fresh smoke from a chemical fire that is burning right now.
And the paper points out this is the first time the methyl radical has ever been detected outside our own Milky Way galaxy.
First time ever. We've seen it in some nearby star-forming cloud within the Milky Way.
Yeah.
But to see it this clearly in a distant ULIRG, deep inside its obscured nucleus, that is a massive technological milestone for JWST.
It proves this kind of reactive chemistry isn't just a local phenomenon, it's universal.
Exactly.
So we've got this amazing list of gases, benzene, the acetylenes, methane, these ghost-like radicals. But the vault wasn't just filled with gas, was it?
No, not at all. The spectrum also showed very strong signatures of solid-state materials.
Yeah.
They saw water ices, which, we might expect to find in that cold outer envelope.
Sure, that makes sense.
But they also found what they call carbonaceous grains.
Which is a fancy word for soot.
Basically, yeah, cosmic soot. Very tiny dust grains made of almost pure carbon.
So paint the picture for me. If I could magically stand inside the nucleus of IRA 07251, which obviously I couldn't, what would I be seeing around me?
You'd be in a swirling, chaotic environment. It's incredibly hot. There are these vast, thick clouds of soot and dust completely blocking your view of any stars. But mixed into that gas swirling all around you are these complex organic molecules, benzene rings spinning past, methane gas drifting by, acetylene chains forming and breaking. It is a chemical soup of an unbelievably high density.
A soup is a great metaphor. But this is where we get to the plot twist in the story. Because normally, if you find a soup, you assume there's a chef and you know the recipe. But when the researchers ran the numbers on this soup, the recipe didn't work.
And that brings us to the puzzle. Yeah. This is where the science gets really, really interesting. Dr. Ismael Garcia Bernete, the lead author, he was very clear about this in the paper. He said the abundances they measured were far higher than predicted by current theoretical models.
And when you say far higher, what kind of scale are we talking about? Is it like 10% more than expected or double?
We're talking orders of magnitude more in some cases. It wasn't a small error. The standard models they use for these kinds of environments, they have acronyms like PDRs or XDRs.
Okay, let's break this down. PDR.
That stands for Photo Dissociation Region. That's a model for a region where the chemistry is driven by intense ultraviolet light coming from young, hot stars. It's the standard way we think molecules are built in a nebula.
Okay. At XDR.
X-ray dominated region. That's a model for a region where the chemistry is driven by high-energy X-rays, usually coming from the accretion disk of the central black hole.
So they took their JWST data, this huge inventory of molecules, and they plugged it into the PDR model and the XDR model, and the computer said?
The computer basically said, error. Does not compute.
Yeah.
The models predicted that the intense radiation in these regions should be destructive. It should shred complex molecules like benzene much, much faster than they can form.
So the models predict a chemical desert, but JWST found a thriving jungle.
A perfect analogy. And whenever you have a discrepancy that massive between observation and theory, it means your theory is missing a key ingredient. There is some engine driving this chemistry that isn't just UV light or X-rays.
The continuous source hypothesis.
That's it. And the real smoking gun for this was the methyl radicals, those fleeting chemical ghosts we talked about.
Right, because they disappear so quickly.
So fast. For us to be able to see so many of them, it means they have to be replenished constantly. There has to be a nonstop fountain of them.
It's like seeing a jet of water suspended in midair, without a doubt that there's a pump running somewhere. If the pump stopped, the water would fall instantly. The radicals are the water in the air.
That's a great way to think about it. So the billion-dollar question for the team became, what is the pump? What is the physical mechanism that can create this unbelievable abundance of complex hydrocarbons right in the jaws of a supermassive black hole and do it without destroying them instantly?
And this is where the Oxford team's modeling really came into play. They started running simulations, trying to find the missing ingredient. They started by ruling things out.
They did. First, they ruled out temperature alone. Just making the gas hot doesn't give you this specific mix of molecules.
Oh, okay.
Then they ruled out simple turbulence, shock waves from gas clouds smashing into each other. While that certainly happens in a place like this, the chemistry it produces doesn't match the specific fingerprint JWST saw.
So they're crossing off all the usual suspects, and they're left with one culprit. And it's a culprit that honestly sounds like it belongs in a 1950s science fiction movie.
Cosmic rays.
I feel like cosmic rays is one of those terms that everybody has heard, but almost nobody really understands what it is. Is it a type of light, like a gamma ray?
That's the most common misconception. A ray implies light, a photon. But cosmic rays are not light. They are physical particles. They are matter.
So atomic bulk.
That's a much better way to describe them. Mostly, they're protons, the nucleus of a hydrogen atom or sometimes the nuclei of heavier atoms, all of them accelerated to velocities approaching the speed of light.
And in a galaxy like this, where are these bullets coming from?
From the black hole itself. As matter spirals into the black hole's accretion disk, the intense gravitational and magnetic fields act like a colossal particle accelerator. They grab particles and fling them outwards in jets and streams at incredible speeds.
So the black hole is acting like a giant machine gun, just spraying the surrounding gas clouds with these high-speed protons.
Exactly. And this leads us directly to the new mechanism they propose in the paper. They call it top-down chemistry. And this, for me, this is the most profound and exciting part of the entire study.
Okay, top-down. Contrast that with what we normally think of, which I guess would be bottom-up chemistry.
Yes. Standard astrochemistry, the kind we see in cold, dark clouds in our own galaxy, is almost always bottom-up. You start with one atom, say a carbon atom, that floats around until it bumps into a hydrogen atom. They stick together. Now you have CH.
And then that bumps into another hydrogen.
Right. Now you have CH. You are slowly, painstakingly building a Lego house, one tiny brick at a time, over millions and millions of years.
It's a slow, steady construction process.
Very slow. But top-down chemistry is the complete opposite. In the nucleus of IRA 07251, you already have those big complex things we mentioned earlier, the soot grains, the carbonaceous dust of large molecules called PAH, polycyclic aromatic hydrocarbons.
So the Lego wall is already built.
The wall's pre-built, yes. And the cosmic rays, they are the sledgehammer.
Ah, I see exactly where this is going.
A high-speed cosmic ray particle, the proton, that doesn't build anything. It slams into one of those large dust grains or a big PAH molecule. And the energy of that impact is so immense that it shatters the chemical bonds holding the large structure together.
It's fragmentation.
It's fragmentation. The big molecule or the dust grain breaks apart. And what are the little pieces that get chipped off? What is the debris?
Benzene, methane, acetylene, the methyl radicals.
The entire inventory, the jungle of molecules that JWST found. It's not being carefully grown. It's the debris from a constant demolition.
That completely flips the script. Our intuition says that high-energy particles and radiation are the enemies of life. They sterilize things, they break down complex molecules, but you're saying that here, the violence is the very thing creating the complexity.
That is the core conclusion of the paper. These deeply obscured galactic nuclei are not just energy sources, they are factories. The black hole provides the power by accelerating the cosmic rays. The cosmic rays are the machinery, and the raw material is the abundant carbon dust.
Did they have proof for this model, or is it just a really elegant story that happens to fit the numbers?
They found a direct correlation. They looked at other similar galaxies, and they found a clear link between the cosmic ray ionization rate which is basically a measure of how intense the cosmic ray bombardment is,
Yeah.
and the abundance of these small hydrocarbon molecules.
The more sledgehammers you have swinging, the more debris you produce.
Exactly. The lines on the graph matched up perfectly. It explains everything. It explains why the old UV and X-ray models failed, because this process has nothing to do with light. It explains the ridiculously high abundance. And it explains the constant presence of the radicals. They're being freshly broken off the large grains every second.
So IRA 07251 is a cosmic refinery. It's taking this heavy, crude material, the carbon dust, and it's cracking it into lighter, more refined, more useful organic molecules.
Processing is exactly the right word.
Which, of course, brings us to the big one. The question every single person listening is thinking right now, even if they know the answers, probably no. We have water, we have carbon, we have energy, we have complex organics. Are we looking at a habitat for life?
I knew this was coming, and I have to be the careful scientist here. The paper's co-author, Professor Dimitra Rigopoulou, she specifically addressed this to, manage expectations.
Let me guess the answer. It's not aliens.
It's not aliens, no. She was very clear that while benzene and methane are organic molecules, they are not themselves life. You don't have a living cell that's made of pure benzene. You don't find DNA floating freely in a hot gas cloud.
But I feel a but coming.
There is a very, very big but. She described these molecules as the products of prebiotic chemistry.
Prebiotic, before life.
The ingredients, the starter kit. To get to life as we know it, to get to DNA, RNA, proteins, you first need things like amino acids and nucleotides. And to build those, you need a ready supply of simpler building blocks like methane and structures like carbon rings.
You can't bake the cake without first having flour and sugar.
Exactly. This galaxy isn't the bakery where the cake of life is being made, but it might be the flour mill, churning out the essential ingredients on an industrial galactic scale.
And this has to connect to the bigger picture of galactic evolution, right? Because this factory isn't a closed system. This material doesn't just stay there forever.
Not at all. Galaxies are dynamic. Supermassive black holes and intense star formation create powerful galactic winds. Supernovae explode. All these processes push material out of the galactic center.
So these clouds, rich with all these freshly made organic molecules, they get blown out into the rest of the galaxy.
They get ejected into the galactic disk.
Yeah.
They drift for millions of years. They mix with other clouds. And eventually, they might cool and condense to become the raw material for the next generation of stars and, crucially, planets.
So you're saying that the carbon that makes up my body, the nitrogen in my DNA, some of it might have passed through a violent cosmic factory like this one, billions of years ago.
It's not just possible. It's looking increasingly likely. We used to think that the chemical complexity of the universe was built up very slowly in these quiet, cold corners. This study suggests that the really heavy lifting, the efficient processing of raw carbon dust into useful organic starter kits might happen in the most violent places in the cosmos.
It makes the universe feel so much more efficient. Even the destroyers, the black holes, are playing a critical role in the cosmic construction supply chain.
It points to a grand cycle. Dust is created in the ashes of dying stars. It gets funneled into the galactic core. The black hole's energy processes it into organic molecules. Those molecules are then spread back out across the galaxy to form new planets and just maybe provide the ingredients for biology.
It's a galactic ecosystem.
Let's talk about the future then. This was just one galaxy, program ID 3368. Is it possible this is just a one-off, a weirdo galaxy, or could this be happening everywhere?
That is the next great question and the most exciting part of this. JWST is just getting started. The paper's conclusion is that this work opens up a completely new avenue of research. Now we know what to look for.
We know what to look for, that specific spectral fingerprint of hydrocarbons and radicals. And we know where to look in the hearts of these deeply obscured, dusty galaxies. We can now start a systematic survey.
We can point Webb at other ULRGs. We can look at active galactic nuclei.
We can check the cores of starburst galaxies. We can begin to map out just how common these organic factories are. And if it turns out that every major galaxy with a supermassive black hole is doing this,
then the universe is absolutely awash in prebiotic chemicals.
it changes the odds, doesn't it? If the ingredients for life are rare and hard to make, then life itself should be rare. But if the ingredients are an inevitable natural byproduct of black hole physics,
then they should be everywhere.
everywhere.
I just want to circle back to the technology for a moment before we wrap this up. We mentioned that false color image they made with the different filters for different wavelengths. It sounds really technical, but what that represents is it's a paradigm shift in how we see things.
It really is. Before we could take a photograph of the vault door, now we're taking an MRI scan of what's inside. We can slice it into layers. We can see exactly where the hot dust is versus where the cool gas is versus where the benzene is most abundant.
And that's why we need to keep building and funding these incredible machines, because looking at this galaxy with Hubble was like staring at a locked treasure chest. Looking at it with Webb, we found the gold inside.
And the gold, it turned out, was carbon, which, for any potential life, is infinitely more valuable.
Touché. So the real shift in our understanding is, it's from seeing the universe as this static, physical place to seeing it as a dynamic chemical reactor.
I think that's the perfect way to summarize the philosophical shift. The old view of space is that it's just vast, empty distances with rocks and stars governed by physics, gravity, inertia. But this new view, the dynamic reactor view, it sees the universe as a kitchen.
A very chaotic kitchen.
A messy, violent kitchen, yes. Things are being chopped up and boiled and mixed. It's not passive. It is actively evolving, not just physically, but chemically.
And we, ultimately, are a product of that cosmic cooking process.
We are the souffle that, against all odds, managed to rise.
I love that. Okay, so let's just do a quick recap of the incredible journey we've been on today.
Let's do it.
We started with a hidden treasure, the Galaxy IRAS 072510248, completely invisible behind a colossal wall of dust.
We used the infrared superpowers of the James Webb Space Telescope to finally pierce that wall.
And inside, we didn't find what we expected. We found a chemical anomaly, a shocking abundance of complex organic molecules like benzene, methane, and especially the elusive methyl radical.
An inventory that all of our current theoretical models said simply could not exist there.
We realized that the slow, calm, bottom-up construction models just didn't work. We needed a constant, powerful source for these molecules.
And the culprit, the engine of the factory, turned out to be the central supermassive black hole itself, or rather the cosmic rays it fires out like subatomic bullets.
These cosmic rays act like sledgehammers, smashing into large carbon dust grains and shattering them into the prebiotic building blocks of life, a process of top-down chemistry.
And finally, we realized that these cosmic factories might be the primary mechanism for seeding entire galaxies with the raw ingredients necessary for biology to begin.
An absolutely staggering discovery.
It really is.
I want to leave our listeners with one final thought, something to sort of, chew on the next time they look up at the night sky.
Go for it.
We have this deep-seated idea that life is fragile, that it needs a Goldilocks zone, not too hot, not too cold. It needs a calm, quiet pond, a safe space to get started.
That's the standard narrative, absolutely.
But this study suggests that the ingredients for life are born in the complete opposite of a safe space. They are forged in the fire. They are the direct byproduct of the most violent, radioactive, high-energy places in the entire cosmos, the immediate vicinity of supermassive black holes.
It's the ultimate paradox. The destroyer is also the creator.
Exactly. So here's the thought. If organic chemistry is this abundant, this easy to make, in the single most hostile environment we can imagine, what does that imply about the rest of the universe? Does it mean that the recipe for life isn't a secret, but that it's being broadcast across the cosmos constantly? That the universe isn't just passively waiting for life to happen, but is actively manufacturing the parts list, shipping it out everywhere, just waiting for a quiet little planet to catch the seeds?
That is a beautiful and a deeply provocative thought. If the seeds are truly blowing in the cosmic wind, then the garden might be much, much bigger and more widespread than we've ever dared to imagine.
I think I'll be mulling that one over for a long time. It's not just light up there, it's a chemical factory.
Indeed it is.
Thanks for joining us for this. As always, keep looking up and keep asking questions. We'll see you next time.
Goodbye, everyone.